Yo, what's up, calculus students? We're getting into Unit 3, one of my favorite units, one of the most important units of this course. And we discuss more of what the slope equation can do for you. Like, if we know the slopes of f, we know how f is changing, how can we maybe analyze the slopes of f so that you really understand what the original function f is doing? So, like, Unit 3, we are going to eventually graph f, and we are going to graph f by analyzing its slopes. If you analyze the slopes of f, you'll actually know how f is changing. If you know how f is changing, you're going to know what f looks like. So it's really fun because it's like completely different than past math classes where, you know, you would just be told, hey, graph f. And you would just like, oh, this is what f looks like. And I would do this. But it's like we were going to look at how f's changing to graph it. And we start off pretty easily. It is something we're going to be doing a lot of in this class. We're finding critical points. Critical points are these locations that are possible max-min locations. What I mean, possible max-min locations. What is a max? What is a min? So, like, if a function goes up and down, we have a max. If a function goes down and up, we have a min. What's in common of these 2 points? The slope is 0. Cool. However, not all slopes are 0. Produce a max or min. So when we find a critical point, which is when a slope is 0 or undefined, we will find possible max-min locations. Okay, slope 0, max-min, slope is 0, neither a max nor a min. And starting next class, we're going to do further analysis to figure out if indeed these zeros are maxes or mins. What? Yes. Shout out. So let's start with this one. It's a quadratic, right? Guess what? By understanding the slopes and by finding when the slopes are 0, you're actually finding the location of the vertex of the quadratic. Now, I should be worrying about when things are undefined. Usually with expressions like this, the only time things are undefined is when we have a slope that has a denominator that equals 0. Now, we don't have a denominator, so we don't have to worry about being undefined for a lot of these. But it's also important to understand that when your slope is a number over 0, that's the location of a vertical tangent. So we are going to see that, these vertical tangents. And a lot of times vertical tangents will not be locations of maxes or mins, but they are critical points. There are situations where we could produce a sharp point. I can think of one type of function that creates a sharp point. This is like the of x squared looks like that. So yeah, so sharp points sometimes will be mins, and you will see zeros for derivatives in the denominator there. Cool. So 2x equals 3, x equals 3 halves. That's the answer. At x equals 3 halves, f has a horizontal tangent. And horizontal tangents, possible max min locations. Now we know, I'm like really distracted while making these videos. We know that this function is a polynomial. It's an x squared. Like I know x equals 3/2 is the location of like the min of that quadratic. But like right now, we don't really care about that. We're going to just say when slopes are 0, we have possible max min locations. When slopes are undefined, we have possible max min locations. What about this one? Well, the slope is 2. We don't have any critical points. Like the slope is 2. Oh, yeah. 2x minus 3 just goes up. So no critical points. There's no maxes, mins. This is just a line. All right, but the rest of them, most of these are just like practice because we're going to be doing so much practice, finding the slope equation, and then factoring to solve. Most of these questions beyond this are all going to be just like this. Making sure we remember how to factor and solve equations equal to 0. If you see these, always look to factor out a greatest common factor. Please do not slide into divide. I don't want you to slide and divide because we need to keep our slope equation intact. It's very important to have this intact in its full entirety. That way we can find specific slopes if we wanted to at any point. And if you like divide by 3, all of a sudden that 3 is gone. And then the slopes that you're going to think you're going to get are not going to be the actual slopes. So don't slide and divide. Don't worry about the divided by 3. That's just 1/3 x cubed. So the 3 comes down, multiplies by the 1/3. You just get x squared. The 2 will come down, get multiplied by the 1/2. You'll get 5x. The 6 will come down. Boom. I just can factor this. I should be checking for undefineds. Now, I don't have a denominator, so I don't have to worry about it. Don't have to worry about the denominator. At x equals -2 and x equals -3, f of x is neither increasing nor decreasing. F of x has a horizontal tangent. At x equals -1 and x equals 3, f of x has a horizontal tangent. It's neither increasing nor decreasing. It's a possible max min location. Keep the 6. Don't let it disappear on you. At x equals -2, at x equals 1, f of x has a horizontal tangent. F of x is neither increasing nor decreasing. When we neither increase nor decrease, we possibly could have a maximum. We talked about it in class that just because you have a horizontal tangent doesn't mean you have a max or min. This is why we say possible. Do more analysis next class. Don't have to worry about when your slopes are undefined because you don't have a denominator. You're going to factor out the x squared and the 4, get that, and I know that there are 2 answers to this. Now, when you factor out 6, 0 is not a solution. When you factor out the x squared or any x's, 0 is a solution. So I have 0, -1, and 1. Possible max min locations where my function is neither increasing nor decreasing. This is a good one. Terminal cosine minus sine equals 0. Don't want to move things. I want to somehow combine things. I want to somehow figure out when this is 0 or undefined. I don't want to divide. I do want to divide by x's. It's tricky thinking about this. This is a situation where, and we solved this in the past, you get tangent equaling 1. So it's like, when is cosine going to produce the same value as sine? This could be negative and this could be positive, or they have to be the exact same thing. Positive and positive, same values gives you 0. Negative and negative, same values, it gets you 0. That's when tangent equals 1. That's at pi over 4 and 5 pi over 4. That's it. I didn't want to do this, but we didn't have to worry about it. Now with fractions, I do have to worry about stuff. I'll show you what I would do when dealing with a fraction. Can I use the quotient rule? Okay, now 0, undefined. We need to solve both of these equations. The top set equal to 0 and the bottom set equal to 0. Now, there's one thing that's good. The bottom set equal to 0 is not solvable. You have imaginary numbers. You get x squared plus 1 equals 0. You get x squared equals -1. We don't have to worry about imaginary solutions. So we say that like the denominator is always positive. We're only dealing with real numbers. So there's actually isn't any values for x where this is undefined. But the numerator, after simplifying, this works out. You get plus or minus 1. Possible max min locations, slopes equaling 0, function neither increasing nor decreasing. I don't know if this one works out very well. I should have done one of those product slash changes. Product slash chains. Oops. Remember, if I put like an X there, then you'd have to use the product rule and the chain rule. You had a lot of those on the AP Classroom. Don't have to worry about when it's undefined, just equaling 0. And again, I get 0 and then plus or minus 1. All possible max min locations. Here we go. All right. Heads up. I'm going to highlight this because a lot of you are not going to do this the correct way. Many of you are going to add a third and you're going to try to solve the equation. But whenever we're dealing with fractions, it's important to like establish a top and a bottom. Don't move stuff. We want just one big fraction. That way can we really identify like when a top could equal 0, when a bottom could equal 0. Let me show you what I mean. We want to use a common denominator whenever we have fractions. I'm going to multiply this by 3 over 3. I'm going to multiply this by 2x to the 1/2 and 2x to the 1/2. That way I'll get a common denominator of 6x to the 1/2. And in the top, I'll have 3 minus 2x to the 1/2. Why do I do this? If we like just added the 1/3 and solved, we probably would forget the fact that there is a denominator and that the denominator could equal 0. So here, we have one critical point at 0. That's going to be a vertical tangent, and that's okay. So we're good. It's a critical point. Now we have to figure out when our slopes are 0. We need 3 minus 2 root x equaling 0. This is when we're going to subtract 3, divide by 2, square both sides. X equals 3 halves squared, 9/4. That's a horizontal tangent. That's what the slope is 0. Okay, so the next two, try to do that same process. Get one fraction where you're setting the top equal to 0 and you're setting the bottom equal to 0 to figuring out when things are undefined or 0. So here we go. Going to multiply this by 3x to the 1/3 over 3x to the 1/3. That way I just have one nice fraction, 2 plus 6x to the 1/3 over 3x to the 1/3. That way I recognize that x equals 0, which is the denominator, equal 0 is a critical point. That's from that. Here, I need to solve this. 2 plus 6x to the 1/3 equals 0. X to the 1/3 equals minus 2/6 or minus 1/3. Okay, now, how do you get rid of the 1/3? Many of you guys know to cube. Why? Because when we take a power to a power, we multiply the powers. When I take a 1/3 and cube it, 1/3 times 3 is 1. That's how I'm going to get negative 1/27th. Cool. Again, these are possible max-min locations. We'll do more analysis next class. We'll actually start human graphing calculators next class with a function just like this. Like x to the 2/3 plus 2x minus 3. Good luck trying to graph that. But wait till next class, you'll be able to. All right, same deal for this. Rewrite it. Common denominator. I'm going to multiply this by 9 over 9 and this by x to the 2/3 over x to the 2/3. When does this equal 0? X equals 0. Just so happens that this is working out this way. Now, when does 9 minus x to the 2/3 equal 0? I don't know. Now is an okay time to move stuff over. How do you get rid of the 2/3? I would take the 3/2 power. Now, what is this? A lot of you like to split it up into two things. You cube it, then square root it, or you square root, then cube. That's fine. You have to square root at some point to solve the equation. When you square root to solve an equation, your solution could be a positive or negative value. Whenever we have an even root, the original guy could have been positive or negative. So, plus or minus is important because of the square root. The square root of 9 is 3. 3 cubed is 27. So my answer should be plus or minus 27. Okay. So that's kind of like really step one. We will then, next class, do the most important thing, which is like a further analysis of the slopes of f so that you know what f is doing. Next class. Starting off with like, can we factor and can we make sure we know how to find the slope equations and set them equal to 0? Easy. Now, Another part of this lesson is the mean value theorem. And the mean value theorem is not tied into Unit 3 at all. This is why I started the lesson with the mean value theorem. It is very much a one-off topic that you need to know. It's actually used for a bunch of proofs in calculus that I don't know or use. So this is just something you need to know that you're going to see on your test. And I honestly could have put it on Unit 2. But your Unit 2 is like so packed to begin with that like I don't want to put extra stuff there. But it's just something that's interesting. If your function is differentiable, then you're guaranteed to have a location where the instantaneous rate of change equals the average rate of change. You're guaranteed a tangent slope equals the secant slope over the interval. You're guaranteed to have a slope of f at some x that equals the slope over the interval. Okay. All you need to make sure is that the function is differentiable, which means it's continuous and it's no sharp points. F is twice differentiable, just means you can take the derivative twice. It just means you have a continuous first derivative. Don't worry about what it means beyond that. It's just like if you can take and find the slopes of the slopes, that means your original slopes are continuous. If you can find the slopes of the slopes, then your first slopes are continuous. Anyways, all this means is there's some x value somewhere, it's guaranteed, at least one, where the slopes of f equals the slope of the secant. This x value is some value between 3 and 5, guaranteed. And we're guaranteed to have that x value where the slope equals negative 13 halves. I don't know why I made it like that. That's what it is. Great. To show that you understand this, I'm going to really ask you the question that I asked you on the test is like, where is the instantaneous rate of change equal to the average rate of change over the interval? But I'm not going to say it. I'm just going to be like, hey, you guys know the mean value theorem? Prove that it works for this function. Well, all you got to do is just make sure that you have a tangent slope at some x that equals secant slope over the interval. This tells you on average how quickly f is changing. This is telling you how f is changing at a moment x. So you need the slope equation. But before finding the slope equation, you need the secant slope. So you don't need the m values, you need the y values. So you need f of negative 2, which is 4 plus 6, which is 10 plus 2 is 12. You need f of 3, which is 9 minus 9 of 2. I'm guaranteed to have an x value where the tangent slope of f equals the secant slope over the interval. I'm guaranteed to have a tangent slope that equals the secant slope, solve, and that value will be in between negative 2 and 3. There's that value. We'd say at x equals a half, f is decreasing by 2 y's per x, which equals the average rate of change of f over the interval negative 2 to 3. Yeah, that's just like, there you go. Guaranteed. by the mean value theorem. All right, so we got f of 1, which is -4. We got f of 3, which is 27 minus 15, which is 12. We got slopes of the tangent. It's guaranteed there'd be an x, where the slope of f equals the average rate of change. Oh, this is the question from your test. It's plus or minus root 13 thirds. However, the mean value theorem guarantees that the value is on the interval, so I'd only worry about the positive root 13 thirds. Don't worry if you put down both, it's like not going to hurt you. Mean value theorem talks about the x's in between your interval. Cool. Get to y values. Remember, y's come from original equations. Remember, m's come from slope equations. So like the average rate of change produces an m over an interval, which is 1. The instantaneous rate of change is found using our slope equation. Slope of f at any x equals 2/3 x to the -1/3. Here's the slope of f at any x, guaranteed to have an x that equals that secant slope of 1 in the interval. I am going to multiply by 3x to the 1/3, but we're not setting it equal to 0. So I get 2 equals 3x to the 1/3. I could have flipped both sides. It's fine. And then cube. And I get x equals 8/27. It's guaranteed. 8/27 is inside the interval. When x equals 8/27, f of x is increasing 1 y per x, which is equivalent to the average rate of change of f over the interval. Let's get our y2 and our y1. y2 minus y1 over x2 minus x1. Get 1/6. When will my tangent slope equal that secant slope? When will 1 over 2 root x equals 1/6? Sides. Square both sides. 9. Look at that. 9 is in between 4 and 16. It's guaranteed to exist by the mean value theorem. And that's where the instantaneous rate of change equals the average rate of change. F is increasing by 1/6 of a y per x at x equals 9, which is also equal to the average rate at which f is changing over the interval 4 to 16. Yeah, I think the important thing about this question is to say these are the intervals. Make sure you see this interval. This is the interval. Now, this is just a visual understanding of the mean value theorem. It's kind of what we started with, the drawing. If I say f from 0 to 3, I see this would be my secant slope. Tangent slope equaling secant slope. Bam, right there. I don't know where that is, but this is my drawing of my understanding of that. From 1 to 3, it looks like my secant slope is practically flat, maybe 0. So maybe we're talking about right there. Just drawing your picture is all you wanted. -1 to 2. This is my secant slope. This would be the tangent slope that equals that secant slope guaranteed. -1 to 2. This is trickier. I feel like we're close to having a maybe like right here, right there. It's cool. Maybe it's like, yeah, that's right there. The following function does not have a point where the tangent slope equals the secant slope. Here's the secant slope, but we don't have a tangent slope that's equal to that. Why does this not defy the mean value theorem? Well, f of x has a sharp point, which means f of x is not differentiable over the interval, which means the mean value theorem is not guaranteed. Isn't that cool? So even if you have a vertical tangent, same thing, not guaranteed, not guaranteed. Okay, good little warm up, and then things get harder next class. But we got this. See you out there. Peace.